So welcome to the session on signal processing for astronomical instrumentation. My name is Girish. I am from the electronics engineering group and also part of distortion laboratory where we are involved in developing sensitive radiometers for precision cosmology experiments. I am mostly focusing on developing digital receivers for these cosmology experiments. So this is what is lined up for today's discussion. You're able to hear me? Right? Clear. Okay. So this is what we have lined up for today's discussion. I'll begin with about 3 or 4 slides where I'm trying to summarize maybe what you have learned through various sessions this week, and then focus on building blocks of a digital receiver like digitization, channelization, and correlation. We'll dig deeper into that, go deeper into that. And digitization is about how you convert a signal from analog to digital. You know, these days everything is digital. There are very powerful processors which can implement complex algorithms. And then it's important to properly digitize an analog signal so that you can process them further. And then different sampling techniques like low pass sampling and band pass sampling. And then channelization. By channelization, what we mean is converting a signal from transforming a signal from time domain to spectral domain. Okay, Fourier transform, obviously, all of you would have heard about that. And then I understand there are 2 special weekend lectures by Professor Deshpande on this. Okay. And then about channelization, and then what are the challenges that you encounter in implementing a channelizer and how you can tackle them using one special ways, or how you can do windowing of the input time domain signal, and then how it helps in overcoming certain deficiencies in channelizer based on FFT. And then we'll also discuss towards the end correlation and autocorrelation and cross correlation. And then we'll also discuss architectures of various spectrometers based on these correlators or a FFT spectrometer. So that's what is lined up. Okay. So we'll begin with this introductory section. So what is the radio astronomer interested in? He is interested in studying natural radio emission from celestial sources by measuring intensity of radio emission as a function of direction in the sky, that is direction in the sky, and then frequency, polarization, and time. Intensity as a function of these parameters. And then he uses, the astronomer uses either a single dish or an array of antennas. This is a picture of a single dish radio telescope. Many years ago, you could see that dish from this particular lecture hall. Now it's not there. This is RRI 10.4 meter telescope. And then if it is an array of antennas, I'm sure you have already been introduced to this. Mayuri gave a talk on interferometry. And then I'll just give an examples of 2 radio telescopes. Our own giant meter wave radio telescope near Pune, where there are about 30 dishes. Each dish is 45 meters in diameter and then spread over 25 kilometers. And then RRI developed L-band analog receiver and a digital receiver unit for this radio telescope. Other one is the difference you can see. This is geometry consists of dishes, whereas here you have an array of dipole antennas. They are grouped as a 4x4 matrix. It's called one tile, and then you have number of tiles spread over kilometers, so that you have large collecting area and different baselines. So digital receiver units for this Murchison-Whitefield array, they were developed here in the electronics engineering group at RRI. As we speak, they are digitizing and then processing signals in the Western Australian desert. So one interesting thing about this MWA is this is a precursor radio telescope for the upcoming world's largest radio telescope, the square kilometer array. Okay, so that's about this. So a quick block diagram of a radio telescope. It has an antenna, analog receiver, digital receiver, control and data acquisition from the digital receiver. Antenna is a passive device which converts the impinging electromagnetic radiation into electric current. It's a weak electric current which is picked up by a specialized amplifier in analog receiver to amplify the signal. And then once it has sufficient strength, there is analog signal conditioning in the form of filtering and passing only the required frequency range of interest for astronomer. And once it is further amplified, it is picked up by the digital receiver, where it gets converted from analog to digital, and then further processing using specialized algorithms like channelization and correlation. So that's what is in the digital receiver. Data from the digital is acquired by this control and data acquisition block. And the telescope control monitor, if it is, for example, a dish or something like that, you want to steer the dish, point it at various directions in the sky, you can have telescope control, and then overall health of the radio telescope control and monitor. And then time reference and distribution system is all of them require local oscillators to down convert signals, heterodyning, and sampling clocks, and then synchronization signals. All these are generated by the time reference and distribution section. Again, I'm sure you would have been introduced to this. Astronomical signals from celestial source and the receiver noise, which is added to the signal by the receiver units of a radio telescope, can be described as time stationary Gaussian noise. That's how it would look, what is shown here. So, for example, here is the zero mean Gaussian noise, and what you see as this red dashed line here is plus and minus 1 standard deviation, 1 sigma. Okay? So, sigma is important here because sigma square is variance. It gives you an estimate of the power in the signal that is entering various sections of the receiver. Okay? So, it is not just this signal from celestial source and receiver noise which is added to that. We also have, unfortunately, what we call as radio frequency interference. These are signals which are from radio and TV broadcasts, satellite communications, various handheld communication, police communication, etc., airport radar communication. So, all these things add, and these are very strong signals compared to this, and they invariably get added. Antenna will not be able to differentiate whether a signal came from a celestial source or it is from a local human generated signal. So, it gets added to that, and it becomes a big challenge operating your telescope in places. So, you typically go to either the site is radio quiet and it's preserved, radio quietness is preserved, or you go to very remote locations to so that the radio telescope doesn't get overwhelmed by these strong signals. Okay. So, radio frequency interference is a big issue in radio astronomy. Okay. So, we will now zoom into and then focus in this talk on digital receiver. There are these 3 blocks in green color. We will focus on them. Digitizer, which picks up analog signal from this analog receiver output, and then converts it into a discrete time series, analog signal to digital. And then channelizer, like we mentioned, transforms the signal from time domain to spectral domain, and then it converts it into narrow spectral bands. There are a lot of advantages processing signals in spectral domain, the frequency domain. And then correlator, it takes these narrow subbands and then produces a power spectrum at the output. There are different architectures of correlator which we will discuss in the last section. Okay. So, that is what we will be. So, we will be going into details of each of these 3 sections in the rest of the slides. Okay. So, the first one is digitization. Okay. Digitization is the process of converting an analog signal to a digital signal. By analog signal, what we mean is it is continuous in time and then infinite amplitude levels. So, in time, for all time it is present, and then there are infinitesimally small amplitude levels. So, when you convert this to a digital signal, you pick up signals, sine waves, for example, here at certain points, okay, and then convert into a number so that you can get a digital equivalent of this continuous time signal. So, how do we do that? You use a circuit called analog to digital converter. It is an integrated circuit that does analog to digital signal conversion. This is a picture of a to D converter, and this is what is inside this. There is a sample and hold circuit. All these blocks will go into details of them. How many of you are familiar with ADCs? Yeah, DACs. Okay, fine. Yeah, yeah.
So why are we converting it into
digital signals? Okay, nice question. You know, one of the major advantages of digital processing with the long back, you will not be converting them into digital signals. You would be having analog filters. Okay. So, one problem with that is the filter which is being designed for one particular frequency range, a set of filters, so that you pass it on for further processing. If you wanted to move to a different band, okay, you have to redesign all those filters. And then there are a lot of challenges in developing analog circuits in terms of choice of components. And then by going to the digital, what advantages that you gain is you are converting analog signal into a set of numbers within a certain range. Okay. So, once you have those numbers, you can use all the powerful digital process. Digital technology has rapidly advanced, and then be it your CPU or your what we call a graphic processing unit, GPU, And then there are specialized processes called field programmable gate arrays, which I'll be telling you more about, I mean not more about. Okay, so when you're doing that, the backend, the digital system, if you just change the analog receiver, if you want to change the frequency band of interest, okay, and then you can digitize it accordingly and then use the same hardware. Whereas if it is an analog hardware, you'll have to redesign it because frequency operation is different. Okay, that is one thing. And then by converting the signals to spectral domain, that is the frequency domain. For example, we discussed about the deleterious effect of radio frequency interference. Okay, so once you channelize there with a specialized algorithm, transformation equivalent of Fourier transform. So if there are particular spectral channels which are affected by RFI, it is easy to drop them off. So just imagine doing that in a time domain signal where all of them are together and you will not be able to differentiate. So there are a lot of advantages processing them digitally, and then the usual advantages of dealing with digital signals. It is repeatable, more stable compared to the analog system. Analog system has a lot of dependence on what we call as IVT, current, voltage and temperature. Okay, this is relatively insulated from that, and then repeatability and reliability is one major advantage. Okay, fine. Anything else? Fine. Okay. So we'll go into the what analog to digital signal converter consists of. A sample and hold circuit, where the sample and hold circuit converts continuous in time and continuous in amplitude input signal to discrete like what we showed here, what is shown here. Okay, and then the quantizer block and the encoder block takes these signals here, which are still infinite in amplitude levels, and then converts it into a number, and then the number converts into digital, and then the number is the digital signal is encoded to produce a set of numbers in a certain range. Yeah. Yeah, we'll come to that. Nice. I'll come to that. I have a couple of slides on that. And then it's very important how many bits. It depends on your end application, frequency range of interest. We'll come to that. Okay. So we'll go deeper into each of these blocks next. Sample and hold circuit is shown in this red dashed box here. Okay, the analog input h of t, and then you just follow this color of this input signal. H of t is a continuous time signal which is shown here, a sinusoidal signal here, and the sample and hold circuit consists of a switch and a capacitor. When the switch is closed, when it is sampling, it follows the input waveform h of t, and when the switch opens, okay, the capacitor is charged to this level and it holds the charge, and the quantizer and encoder converts the signal to a number. Okay, so what's happening here is, and then this operation of the switch is controlled by what is called as the sampling clock. Sampling clock we can relate it to as a series of train of delta functions with the spacing of Ts. So for example here, what we've shown here is in analog signal shown in red here, it's sampling, it's analog signal of frequency 26 megahertz approximately, time period is 38.4 nanoseconds. And what you see in the black here are the delta functions which are picking up signals at discrete time. What is continuous has been discretized so that you have samples only every 2 nanoseconds because the sampling clock is 500 megahertz. Okay. I may first, if there is somewhere you are not understanding, please stop me. And, okay. So at this point, it is still, the signal is ranging from minus 0.17 to plus 0.17 volts peak to peak. So once it gets to this quantizer and encoder, it converts this number from minus 1.7 to plus 1.7, what is called as the scale, full scale range of the A to D converter. Then the quantizer has, in this example, converted those numbers from these numbers to a set of numbers from 0 to 102, 1000. Okay. So the red one cycle is time period is 38.4 nanoseconds, and the delta function is spaced 2 nanoseconds apart. So 38 by 2 nanoseconds, approximately 19 samples in one cycle. If you just count this, you will have approximately 19 samples in each cycle. Okay. So just be aware that this is heavily oversampled. We'll come to that, what we mean by oversampling, undersampling. Okay. Yeah. We don't really have to modulate the signal because, yeah, we can amplify the signal. No need to modulate the signal. will amplify the signal. So most of the effort will be in trying to preserve the signal which came from celestial source as it came in the receiver system. That's going to be a major effort to retain it as it is, and not bring in any artificial thing into it. So, but still, I'll just come to in the next slides. Quantization is not perfect. There will be some things added to that, and what is called as quantization noise. Okay. So we discussed what is this sample and hold. We'll just get into now details of this encoder and quantizer. So there's this output voltage present at the across the capacitor. It is fed to this is the quantizer. It is fed to where there you have a series of comparators here, and the one input of the comparator is the output of this capacitor. That's the voltage across the capacitor. Other input is the threshold is various reference levels, which is obtained by this ladder network, which is reference to a voltage reference here. So as soon as signal, whenever a signal is higher than the threshold, from that particular comparator there will be a 1, like what you see here, and then where it is less than the threshold, it will be zeros. So this is called as a thermometer, digital thermometer code. So this is passed to the encoder, which generates a binary output of this, so that you'll be able to process in a computer or a digital processor. Okay. So just one example, x-axis here is the analog input signal, and then y-axis is the digital output code, which is basically summarizing what we discussed about the A to D converter architecture. So as the input signal increases, it produces various codes, and then for one range of this here, all codes correspond to this analog input range is just this one code. So because of which you will have error, quantization error. Okay. So for this particular example here, red is the analog input signal, and because it has 3 bits, B is 3 and then 2 to the power 3, you can represent 8 different levels. Okay. So you have the entire sine wave is represented here by various codes which corresponding to all zeros to all ones, that is 0 to 7. Okay. So in this particular case, you are asking this question, there are numbers ranging from 0 to 1024, 0 to 1023. So obviously B was 10 here, 2 to the power 10 is 1024. So that is what. So A to D converter, important ADC parameters is bit precision. So in a case where, so the thing is, the challenge in implementing a flash A to D converter is, so if you have, if it is a 3-bit A to D converter, you need 8 comparators. If it is a 10-bit A to D converter, you need 1023 of them. Okay. So increasing the number of bits and providing higher sampling clock, all these things becomes a design challenge in analog to digital converter. Yeah.
The signal strength is very low, then
Yes.
we have to compromise with the quality of the signal.
Yes. So that is one of the reasons why brought in the concept of sigma variance, sigma square. So, and then depending on the level of radio frequency interference which is coming in, and so you adjust the signal power level by adjusting the gains in the analog receiver. So that, so this is the step size, quantization step size. Okay. If you don't have sufficient strength in the signal, this, for example, if this red sine wave was much smaller, it had occupied only say couple of quantization, obviously you are not doing right job. So that is why one of the important ADC parameters is ADC full scale input range. Okay, you amplify your signal in such a way that it occupies significant number of quantization levels. Typically radio astronomy is comfortable working with 4 or 5 bits, and the rest of the bits is assigned, is left as headroom, so that when there is a strong radio frequency interference, your ADC does not get saturated or overwhelmed by it. Okay. Is there any question on? So what you see here is ADC is a nonlinear device. In a hypothetical case where number of bits is infinite, only then, and then you will have very small quantization step size, only then it will follow this red original analog signal. Okay. So we spoke about that sample and hold, and there is this clock to the A to D converter. Okay. so which is operating that switch, which is charging the capacitor and then holding it for conversion. So how fast should it operate? That's the question. So here we have an example where the analog signal is 7 kilohertz of frequency, and then if you are sampling at 6 kilohertz, what happens? So 7 kilohertz, and then time period is 0.14 milliseconds to complete one cycle, and then the time period for 6 kilohertz, the sampling clock is 0.16. Obviously, you can only pick up one sample from each cycle. So these are the samples which have been picked up from each cycle. So if you fit a sine wave to these samples here, it appears what is seen in light gray as 1 kilohertz. So although your input signal was 7 kilohertz, what you finally get out is only 1 kilohertz, which means you are not properly sampled it, and what is called as aliasing is happening. This is how you visualize aliasing in time domain. I'll also show how it appears in frequency domain in the next slides. Okay. So instead, if you had a 20 kilohertz signal and then you had sampled it at 40 kilohertz, so you are picking up 2 samples in each cycle, and then you will be able to reconstruct the sampled signal properly. Okay. So yeah.
How are we getting that as 1 kilohertz?
Yeah.
I mean, that's
Yeah, if you compute from the time series here, from the this is 0.1428 milliseconds, one cycle, and then this has 1, 2, 3, 4, 5, 6, 7 cycles. Okay, so if you compute that, that comes to 1 kilohertz. Okay. Yeah.
If signal which we are receiving is periodic only, then we can use this Fourier.
Yes. Yes.
If it is not,
We'll come to that. Okay. Obviously, signal that we are trying to receive is not only it's not periodic. It is a, we say, time stationary Gaussian signal, which has the signal from source which is embedded in it, and then how we pull it out, and then what are the challenges you encounter in Fourier transformation. We'll come to that. Okay. So at what rate should that sampling clock with the switch operate? That's the question. So that was addressed by this Nyquist-Shannon sampling theorem, which is an essential principle in digital signal processing, which links the frequency range of the signal and the sampling rate. Sampling rate by which, at what rate should the switch operate, which is required to avoid this distortion called alias. Okay. So the theorem states that the sampling rate must be at least twice the bandwidth of the signal. So for example, here, like you see here, it's 20 kilohertz. If you are sampling it at 40 kilohertz, then you will be able to reconstruct the signal. And then if you are not maintaining 7 kilohertz, ideally the sampling clock should have been 14 kilohertz at minimum. So because it is not there, then you have aliasing here. So, so this helps us in arriving at what should be the rate at which the sampling clock. Yeah.
If the signal is not periodic, still you can reconstruct.
Yes, we'll come to that. This is an example, so that I didn't want to straight away go to a band of signals, which obviously from radio astronomy point of view is a random signal. Okay, I'll come to that. This is just to it is easy to visualize aliasing when you know these frequencies. Okay, I'll come to that in the next couple of slides. Okay. So if the sampling clock is 2B, then it is called Nyquist rate of sampling. That's what is seen here. Okay. And then just be aware that it is not really equal to 2B. It's, in practice, it is always slightly greater than 2B. Reason is, if even though it is, we are picking up 2 samples here, if you just slide this analog signal, if you are picking up at 0 crossing, okay, so you will wrongly conclude that there was no signal. So if you are slightly more than 2B, then you will pick up at some point of time a series of sine wave samples. Okay. Okay, so we'll come to band of signal band, okay, and then not necessarily periodic signals. Obviously, we are not dealing with periodic signals here. Okay. So the concept of band limited signal is important here in terms of sampling. Okay, so this is a low pass signal, which means it is beginning from 0, and then there is a cutoff at B. So beyond B, if it is, when you say it's a band limited signal, that is in theory, it is, there is 0 strength of signal beyond B. But in practice, it cannot be that way. B will be at a level of 25-30 dB, which for most practical applications, the signal is attenuated such that it doesn't really matter when you convert it from analog to digital. So for this example here, if we take B as 2 kilohertz, and then in the plot B here, B is 2 kilohertz. If you are maintaining a sampling rate of 6 kilohertz, obviously Fs is greater than 2B. We are more than the required Nyquist rate. Fs is 6 kilohertz, Fs by 2 is 3 kilohertz, and then this B is at 2 kilohertz within this, and then there is what is called guard band between the Nyquist band, that is Fs by 2, and then the next band here. So what happens if you still maintain the sampling clock at 6 kilohertz, but if the B extends to 4 kilohertz, like what you see here, that B here is at 4 kilohertz, sampling continues to be at 6 kilohertz, then you have this, the edge of a portion of this band and portion of this band overlapping. That's what you see here. So even if it is not a periodic signal, if it's a band of signals, okay, you will have aliasing if you don't choose proper sampling clock. So it is to reduce aliasing, you can not do away with aliasing at all in practice. So to reduce aliasing, you use anti-aliasing filter before the A to D converter and choose the correct sampling clock. Okay. Yeah.
How do we account for thresholding?
Okay, thresholding, one way of looking at it is when you attenuate a signal by about 35 dB, okay, it is 1,000th of the signal in the peak of the passband, okay. If the voltage is much lower than the quantization step size in the A to D converter, one easy way of looking at it. So it doesn't produce any output codes at all from the A to D converter. That one way to look. So it is below quantization noise levels. Yeah, you had the question.
Why should we reduce aliasing before?
Yes, nice question. Okay, I was about to come to that. So this is a this is a low pass filter here going up to B. Just imagine there was no low pass filter, or even if there was a low pass filter, and then just below Fs, if there was a radio frequency interference very strong, despite you attenuating by 30 dB, it was so strong that that signal was somewhere at this level. Okay. So Fs minus, all these things fold back into this. Okay. So very careful choice of anti-aliasing filter. This is a low pass filter, and choice of sampling rate.
So this helps us to correct the noise from the signal.
No, the radio astronomy perspective, this band contains a signal which is time stationary Gaussian. Okay, so it is trying to avoid other components in the spectrum which is at the ADC input getting back, folding into our signal of band of interest. Okay, fine. So this was about a band limited signal, which is a low pass signal going from 0 to B. So what happens if the signal is again a band limited signal, but not starting from 0, but there's an offset. So it is an FL and FH, F low and F high frequency. This is called a band pass signal. So Nyquist rate said you should sample it at 2B. So for this particular example here, bandwidth is 100 minus 60 is 40 megahertz. Is it okay to sample it at 80 megahertz? We will see whether 80 megahertz is the right sampling clock or not. Okay. So for band pass signal, these are the requirements of band pass signal, unlike a low pass signal where it is 2B, meaning at least 2B. Okay. So bandwidth here is 100 minus 60 is 40 megahertz, and then bandwidth should be less than or equal to F low. 40 megahertz is obviously less than 60 megahertz. This box is ticked, and then you need an integer n here. 2 obviously is beyond the Nyquist rate and beyond, and then FH by bandwidth here is 100 by 40 because it is an integer. N is only 2 for this particular example. Okay, so you plug in this n equal to 2 in this valid sampling frequency range. If you calculate here, you will get 100. The valid sampling clock ranges from 100 to 120. It is not 80. So band pass signal sampling, band pass sampling has specific requirements. Otherwise, if you have a signal sampling clock at 80 megahertz, you will be aliasing the portion to the right of it into this. Okay, so you need to be careful with the choice of sampling clock for band pass. These are the requirements for band pass sampling. Is there any question here? Yeah.
Can we just shift the signal to a low pass, like shift it?
Yes. Yeah, that is possible. You can have pass it through a mixer and a heterodyning circuit. Okay, so you have a local oscillator, a mixer, and then beat it to low pass signal. So generally we always want to avoid that because of various challenges that one faces when you are implementing that. this is 40 to 100. So you have a local oscillator beat this signal, and then you can bring it to 0 to 40 megahertz in a low pass filter. Okay. A mixer is again a nonlinear device. Okay. And so this is called the RF input port, this is the local oscillator port, and this is the IF port of a mixer. Typically there is limited isolation between these ports here. Local oscillator at some level can get into this, leak into this, that's one problem. Okay. And you want to avoid this because it's a nonlinear device, and you will generate, make the system more complex. You need a local oscillator circuit which is generating these. Okay. And one of the most important things apart from all these is ADC technology is improving. One of the important parameters that we saw, which is listed here, is analog input signal bandwidth. Modern A to D converters are what are called direct RF sampling A to D converters. You can avoid this analog system altogether because it has an analog bandwidth which is capable of, modern A to D converters have an analog bandwidth which can go up to 16 gigahertz. So you can do away without this analog setup. A nonlinear setup, it requires additional, you require this down conversion, you require generation of local oscillator. So these days the trend is to do direct RF sampling. It has its own challenges involved. So did that answer your question? Yeah.
Like if the input signal also have phase, can you still use this low pass and band pass?
Yes. Yes. So that's what interferometry is all about. You release all of the antennas elements processing at the same time. That's why it's a one of the major blocks which was shown was synchronization and time reference distribution. Okay, so you can operate it in interferometer mode, and then you can release the sampling clock of output from all antennas at just at the right time. Okay, and then so you can maintain, you can get the phase of signal which is coming in at various antennas. Okay, so that was about bandpass sampling. So we go to the next section, which is channelization, which is transforming signal from time domain to spectral domain. Some of your questions will be answered in this section. Okay, so we have something called what's called as an analysis filter bank, also known as channelizer or F engine, Fourier engine. Okay, and it consists of a set of parallel filters to split the broadband input signal into narrow subbands. Okay, so we discussed, somebody asked why do we need to work in the frequency domain. You split into narrow subbands. If there are radio frequency interference channels, you can flag them out. Okay, and then process signals which are bands which are clean. That is one advantage that you have, and there are a lot of advantages working in frequency domain. Okay, so most radio astronomy radio telescopes have this channelization in some form or the other. Okay, so synthesis filter bank is takes in multiple parallel bands and then converts it into one broadband signal. So this input and this output will, in theory, can be similar. Okay. So channelization is routinely used to facilitate improved computational efficiency whenever you are analyzing or processing a signal. Okay. Yeah, Nicholas.
What actually happens in synthesis?
Yes, we'll synthesis. Equivalent of like what you see here. Forward A50 or forward Fourier transform, inverse Fourier transform, right? You get back your time domain signal. Someone had no? Okay. So this is a busy slide. We'll spend more time on this. Like I mentioned, you will have two dedicated weekend advanced sessions on Fourier transform. For the time being, we'll just see that this Fourier integral. Analog signal x of t, to transform it from time domain to spectral domain, you use this Fourier integral. So we have already digitized this analog input signal at using the A to D converter. Okay, so we are working with not with analog signal, we are working with discrete time series. Okay, so you can't use this, you can't go from minus infinity to plus infinity at all time. So we use what is called as discrete Fourier transform. which is given by this. X of n is the discrete time series, and you multiply with this e to the power minus j 2 pi by n nk. You can use Euler identity there. So you're basically multiplying it with a set of sinusoids and cosinusoids, with multiplying that with the input signal over this n is equal to 0 to n minus 1, n samples. If input sample, the length of the input sample is n, and if you have been sampling at fs, when we discuss the time domain aliasing, we discussed that if somebody gave you a set of numbers and then said this is a sine wave, I have digitized it, without telling you what was the sampling rate, what was the filter, anti-aliasing filter, you will not be able to make out any, you will not be able to say what was the frequency of the sine wave. Like we saw, it was 7 kilohertz and 1 kilohertz, both of them were similar. So if you are not given additional information like what is the sampling rate and what was the type of filter which is used, it is difficult to make any sense out of that. So here, if you have a sampling clock of 1 megahertz, and if the length of the time series is 64, this analysis frequency provided by fs by n, 1 megahertz by 64, then you, for every m here going from 0 to 63, you will have frequencies called, what are called analysis frequencies. For m is equal to 0, obviously it is 0. For m is equal to 1, fs by n is 15.625 kilohertz, and then it goes on like this. So the reason is, if you had an input signal to the A to D converter which was at 46.875 kilohertz, if you had sampled it at 1 megahertz and then you discrete Fourier transformed it, okay, so this is how that samples look like. These are the discrete samples there. But these analysis frequencies ranging from m is equal to 0 to n, you multiply all of them, each one of them, as you expand this, you can make this as a matrix, n by n matrix if you expand this. Okay. If you multiply with them, except for analysis frequency m is equal to 3, for all others, okay, it will, the summation will be 0, because the integral cos into sine, something like that, with where m and m of the cross and sine are not, they will integrate to 0. The summation will be 0 here. So basically you are looking at something like a correlation between input signal and the m analysis frequency. Wherever it matches exactly, by exactly what we mean is there are integral number of cycles within the samples of 0 to 64. Okay, so you can see there is 1, 2 and 3. The next sample will begin for the next cycle here, and all analysis frequencies are also integral number of cycles. Except for m is equal to 3, all other places you see that the summation is 0. Only for m is equal to 3 here. Instead of 46.875 kilohertz, if the input signal was 62.3, only for m is equal to 4, you will have tone present, okay, energy present at this. All others will be 0. What happens? Interesting thing happens if it is something between 46. The signal which is coming from outside, you have no control over what frequency. For example, a radio frequency interference, you have no control over what frequency is coming into your band. If it is something in between these two, between m and m is equal to 3 and m is equal to 4, for example, 52.125 kilohertz. So what happens is, you can see that it has 3.4 cycles, it does not have full cycles, but m is equal to 4 here. When you do that, for all m analysis frequencies, okay, you have some energy or the other. It is not 0, unlike this. So there is no, and then this is called as spectral leakage. When it is between between two m's here, the signal leaks into other spectral channels. Okay, this is called spectral leakage. There is no spectral leakage as long as the input tone is centered on one of the bins, when it is m is equal to 2, 3, 4 or something. Okay, yeah. What is this? M parameter is, m is, so the length of this is n, going from 0 to n minus 1, 64 here, it is 0 to 63. So m into fs by n, these are called analysis frequencies. Okay, so basically what this discrete Fourier transform is doing is, you can look at it as correlating your input sequence with various sinusoids for m is equal to 0 to m equal to 63. Okay, you can look at it as a correlation. Wherever these two frequencies match, you will have tone here. otherwise it is not present. Okay. But what happens if the tone is between two integers, in between two of them? So this leaks. So that is called the spectral leakage in DFT. Okay. So before we leave, is this clear, or is there any questions? Are there any questions on this? Okay. So before we leave, just want to say that FFT, fast Fourier transform, is a computationally effective algorithm to compute this DFT, and then this is by these two, James Cooley and John Tukey, in 1965, and with advancement in processor technology and then various specialized processors, FFT is used in some form or the other in transforming signals from time domain to spectral domain. Okay, most radio telescopes use this, and then DFT through FFT is one of the primary tools which is used in signal processing. Okay, so why did we have that spectral leakage? That's what we are going to address in this slide here. So on its own, the discrete Fourier transform does not make a good filter bank, especially when input signal is between two m's, for example, m is equal to 3 and 4 like we saw. The discrete Fourier transform can be rewritten like this signal. You see that you introduce this W of n here. It's a window function. When you don't explicitly specify a window function, it is like each x of n time sample being multiplied by 1. So if it is multiplied by 1 here and then it is 0 outside, in this long time series, if you just pick up one section of that, so Fourier transformation of this rectangular function here gives this frequency response here. And then you can see that there is a main lobe and there are side lobes with certain roll off 20 dB per decade, and then the problem here is that the peak level of the side lobe is just about 30 dB, approximately 13 dB below the peak here. So that is the reason why you see this spectral leakage across all spectral channels. Okay. So why did this happen? It is because of this abrupt change from 1 and 0. Okay. So if you don't explicitly specify a window function, it is considered a rectangular function. It is implied. Okay. So every time you take a Fourier transform, DFT or FFT, rectangular window function is implied if you don't take care. Okay. So what can we do to reduce the effect of, what can we do to reduce spectral leakage? So instead of an abrupt change from 1 to 0, okay, if there is a smooth transition from 1 to 0, okay, input signal multiplied with this window, so this is the windowed signal, so there is smooth transition. What you see is different windows here, and then it just depends on how they transition from 1 to 0, various shapes, okay, and their corresponding Fourier transforms are here. Red, what you see here, this is the rectangular function. You can see it has a main lobe, and then it has side lobe, and then there is a roll off. So by choosing different window functions, you can control the adjacent channel, the side lobe leakage, and then the roll off. For example, for this, what you see in purple here, it's a Blackman et al. Window, which is shown here for 4 FFT bins. Okay, just compare this with the 4 bins of rectangular function. It has a narrow main lobe, but the main lobe is increased here. Okay, that causes loss in spectral resolution. Okay, but side lobe at 13 dB level, that is improved to about 100 dB. This is multiplication of input signal in time domain. Equivalent of that is convolving the spectral response of this with the input band. Okay, so maybe we are not discussing convolution right now. Okay, so that is what, not modulation. It is multiplication in time domain and convolution of this these two spectra. That's the incoming input signal band and the transform of that, and the window function, the frequency response of window function, they are convolved in frequency domain. Okay. So you see that you can reduce the leakage by using various windows, but the price that you pay, like I said, is the main lobe has widened. Okay, and so that you can see what is happening is you will not be able to distinguish here if there were 2 tones corresponding to this m is equal to say 3 and m is equal to 4 here, if the spacing was x kilohertz, okay, here that spacing it will be much wider than x kilohertz. So your spectral resolution is reduced. Okay, that's a price. And then there's one other important thing. What you see is towards the end on either side, you're downweighting the input signal. So what that does is it reduces your sensitivity of your final detected signal. So there are techniques where you can recover that sensitivity, but it comes at the price of a complex circuit. Okay. So instead of a window function, if you have a filter before you do a Fourier transformation, okay, and then the length of this filter is such that it is not just window function was if it was n samples which are being Fourier transformed, the window function is also n samples long. If this is k times n, where that k may be 4 or 8 times 64 into 8, if they are the filter coefficients, then you can control the shape of the filter, and you can almost arbitrarily control the shape of the filter, and then you see. So this approach is what is called as a polyphase filter bank. This is what is routinely used in most modern radio telescopes. Okay, quality of filters implemented and the ability to oversample allows the polyphase filter to be cascaded to get higher resolution. So it allows arbitrary filter response to be implemented in the correlator. So you can see there's a passband is flat, whereas here you can see what is called as the picket fence effect in Fourier transform. Okay, DFT for a rectangular window. So band is flat, and then you have at the same time you also have a good side lobe rejection. So we'll come to the last section now. It's the correlator section. So we'll be discussing autocorrelation and cross correlation. Autocorrelation is a measure of measures the similarity between a signal and a delayed version of itself. X of t is signal, and then it is displaced by tau here, and then there's integral of this to give, and then autocorrelation function is a function of displacement here, tau. We'll see this pictorially how it works. The original function is this, ranging from minus t by 2 to plus t by 2. If it is displayed such that this is beyond minus t by 2, obviously the integral there would be 0. As you slide it, and there is the overlap is increasing, and then when there is no displacement, this is exactly following that, then you will have the where tau is 0, you are multiplying this to x of t into x of t, that is the maximum value of the autocorrelation function, and then once you go beyond t by 2, and then the autocorrelation function is again 0. Okay. So this is how this is the pictorial representation of autocorrelation function. It helps identify periodicities and repeating patterns before instead of this band here, this is all x, and then ranging from minus t by 2, it was a periodic signal, for example sinusoidal signal, and then output will also be sinusoidal, and then it will always, even if the input is sine, the output will always be a cos of some function. Autocorrelation function will be cos, and then it is symmetric, always symmetric about the y-axis. Maximum value occurs, you can just look at it when tau is 0, that's the maximum value that you can get from that integral. And for an aperiodic signal, depending on the temporal structure, what happens if it is an aperiodic signal? For example, like what is ranging from minus w to plus w, if it is a band of if it was a white noise which is passed through a filter, okay, how does the autocorrelation look like? So it is white noise. If there was no filter, it is truly random, okay, and then if you pass it through this filter here, okay, as you increase the tau, that is displacement, because it is random in nature, you don't expect correlation with that signal, okay, so the correlation falls off very quickly, okay. So we'll just remember this, we use this in the next couple of slides there. So that if that was autocorrelation, then cross correlation is a measure of similarity between two signals as a function of displacement of one signal relative to another. X of tau, h of tau plus t, t is the displacement here. This is x of t, h of t, h of t signal is displaced. Again similar to that, you integrate, that's multiply, and then get the area there. Once it is beyond a on this side, then correlation is 0. Just like autocorrelation, unlike autocorrelation, in general cross correlation is not even function like what you see here. It's not, okay. The location of the signal, location of the peak in cross correlation, if your if this had more of different minus t by 2 to different 2, if all of them had, if it was a series, and then if you did a cross correlation, you will find, you have to find the periods of each of the pulses. The pulse period could be detected from this. And then for a particular delay, they will all overlap. Then you know what was the delay which caused that, and then you'll be able to measure the period of the input signal. And importantly, this is what is used in most radio telescopes. Enhances the signal to noise ratio when detecting a signal hidden in noise. The correlation process emphasizes the similarity between the signal and the reference while attenuating uncorrelated noise. When noise is uncorrelated, obviously the integral or the summation there goes down to 0 or reduces to 0, but if there is periodicity, that will show up. That is seen here in this example here. If you have a signal x of t with a random component and periodic components together, if you do an autocorrelation function of this x of t, r xs of tau, you have the random component which we saw that it with the delay with the displacement the correlation falls down, but because of the hidden periodicities here, periodic signal produces output is also periodic correlation, so this stands out, whereas the random component goes down. Okay. So intensity as a function of position in the sky and then frequency. When we come to here as a function of frequency, that is, you are trying to get an output where x-axis is frequency and then y-axis is strength at each frequency point. Okay. So power spectrum density, that is what you want from a spectrometer. Okay. So before advent of efficient FFT engines, spectrometers were designed based around the correlators implementing the functions that we just now discussed. Okay. So this operating principle is based on what is called as the Wiener-Khinchin theorem, which states that the power spectrum of a signal is the Fourier transform of its autocorrelation function. Fourier transform of this autocorrelation function x r xs of tau, if you take that, gives you power spectral density. That is the Wiener-Khinchin theorem. If you have a signal time domain signal, you pass it through, you implement autocorrelation function of that, and then Fourier transform it, you get intensity as a function of frequency. So this is one way is to get power spectrum here. If from this time domain signal, you can just take Fourier transform of that, and then for each complex output you can get power out of that and still get power spectrum. So there are two ways in which you can get power spectral densities. So one is based on correlators, other one with rapid advances in digital technology using high-speed A to D converters, feed programmable gate arrays, specialized processors for implementing DSP algorithms, and our regular processors. Okay, allows efficient computation of FFT in real time. Okay, you can almost compute million point FFTs in no time these days. So this has led to development of a reliable and robust FFT spectrometer passing through this path, taking this path. Okay, time domain, Fourier transform, and then getting power spectral density. So these two ways of getting power spectrum. Correlator refers to a digital device that accepts basically the same integral to accept two streams from two A to D corresponding to signals from two antennas, okay, and completes the correlation of the two signals. A correlator is at the heart of most modern radio telescopes. Okay. The two fundamental operations of the spectrometer are Fourier transformation and multiplication, like we saw, called F engine and X engine. Depending on the order of f of x, f and x, it could either be a xf correlator or an fx correlator. In an xf correlator, you first do the correlation. This d here is the digital delay. This is equivalent to the tau in the integral there. Okay, and then you have various displacements or lags, and then you multiply the one signal from antenna which is undelayed, that is x of t, and then y of t plus tau from this other antenna, and then this accumulated and then Fourier transform to get power spectrum. This is an xf correlator. In an fx correlator, signals from two antennas are first Fourier transform and then multiplied to get cross power spectrum. So this is the architecture of a fx correlator. I just end with this couple of pictures. So at RRI we have developed the spectrometer based on xf and fx correlator. This is an autocorrelation spectrometer, whereas this is a A to D converter. This is a signal processing platform, A to D converter, and field programmable gate arrays, where you implement this Fourier transformation and this correlation inside this FPGA. Okay, so this is a FFT spectrometer. And I'll just conclude with this last slide. You will maybe hear more from Uday, who will be speaking on in the weekly advanced session on SKA. So SKA will have about 1,31,000 antennas. We are only talking about one antennas, and 1,31,000 dual polarization antennas. So it is about 2.6 lakh antennas. Each antenna is digitized Fourier transform. So you can imagine the complexity in that is in the what is going to be the world's largest and most powerful radio telescope, which is going to come up in Western Australia. Okay, so so in a tile consisting of a matrix of 4 by 4, you can digitize each of the two antennas, both polarizations, and then do equivalent of a Fourier transformation polyphase filter bank. Then you can do a lot of signal processing like beam forming, cross correlation, and further processing inside this. Yeah. Sorry?
There was a radio telescope with respect to
Chandrayaan 3? No. That was UVIT, and earlier to that was AstroSat, which was X-ray telescope. And there was one radio telescope, one X-ray telescope from RRI, Polix. Yeah. Okay, fine. I think I'll end here 1 hour. Thank you. If there are any questions, we can take it up. Correlation function looks like a did you see that in any of the slides here? Autocorrelation function. X of t plus tau. So if input signal is a random noise like this, it cannot be a delta function. It will be a function like this, like we saw here. Here, it's a correlation function goes like this. Correlation falls off rapidly because with delays, the signal you don't expect, you expect because it is random, you don't expect it to be correlated. So correlation function falls off quickly. Okay, you're right. In the hypothetical case where this minus W to plus W goes to infinity, obviously everything gets concentrated. So it means highly correlated signal. Okay. Then it becomes a delta function. To that extent, but you can never have that in practice.